Hello everyone. We're starting a free open lecture in our Discord. All our lectures are held weekly without interruptions. If you, the viewer, want to ask questions and get answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. To find out the schedule for the lectures, join our Telegram channel. Today we have the G3 Diva problem. The problem is called tree destruction. The time limit for the test is 2 seconds. The memory limit is 256 MB. You are given a tree with vertices. You can choose two vertices A and B and remove all the vertices on the path from A to B, including A and B themselves. In this case, A can be equal to B, meaning it can be the same vertex, just a double. So what needs to be done? Find the maximum number of connected components that can be obtained after removing the path from the tree, like this. So we have the constraints here. At 10 to the 4, n2 to the 10 to the 5, weld on n2 to the 10 to the 5, and there's a description of the tree. The answer for each test is a single number. Basically, if we summarize, we have a tree with n vertices. There are n vertices and n edges. You need to choose vertices A and B, which can be the same vertex. All vertices are removed on the path between A and B, including A and B themselves. You need to choose these two vertices in such a way that you get the maximum number of connected components. You need to output their quantity. A connected component, well, in this situation, it's the number of trees formed, meaning that after removing the path, we will have a forest of trees, and we need to find the largest possible forest. There are as many separate trees as possible. So let's go through some examples. Well, let's say we have a tree. It looks like this, like a bamboo, and then there's a small split. Here, we have some designations right away. The green ones are the vertices that remain after removing the path. The purple ones are the vertices that we will actually choose. These will be A and B. The red colors indicate what to remove, which I will connect with the purple ones. Well, it's clear that the vertex also gets removed, but for such a tree, the optimal way would be to remove everything between vertices 3 and 2, meaning those vertices themselves, and the choice between them creates three components, vertex 4, vertex 5, and vertex 1. Well, this will be it 3. Next, let's consider this example. From there, we have 6 vertices that are not connected in this way, and the optimal choice for us would be to select vertices 1 and 3. In this case, we will have 2 components left on the side of the troika, free countries. The units are also 2, so we get 4 more. There's no way to survive here, but basically, if we have 2 vertices, the maximum can become 4 out of 6. And the last example we have is like these legs of a body, so to speak. This is how the tree turned out, to be drawn with 6 vertices. The vertices that will be optimal to choose here are vertices 3 and 1, 4, and everything in between on the path. Remove. So it turns out that vertices 3, 2, and 4 are being removed. Vertices 5, 6, and 1 will remain, each of which will be separate connectivity components. So the answer is, in the end, it turns out 3 for this example.
Do you want to become a cool programmer? Subscribe to our Telegram channel.
Well then, thank you. We move on to the solution. So the first thing I'll point out is that we will only suspend, well, our tree, as you can see, is not suspended by anything, not even by the one that we can choose for ourselves. Even if it was suspended, we could change it as we wish. Well, for convenience, it is better to hang the tree here by the top, which is not a leaf. A vertex with more than one neighbor isn't a leaf. In this graph, only vertex 2 can suspend the tree, as vertices 1, 3, and 4 are leaves with one neighbor each. Considering the presence of leaves is important, but solving the problem simplifies things. Theoretically, we can suspend it from vertex 2. This approach clarifies the situation and addresses potential challenges. But while I was solving the problem, it seemed to simplify a lot of things. Because if we have, well, in theory, a flow, we can say that we can suspend it from there. For her, the answer was to read in a not very convenient way. So what else can be noted here is that this is dynamic programming on trees. And accordingly, for this dynamic programming, we get 4 arrays that will solve 2 subproblems. What data arrays do we have? Adaptable. It's like the dynamic programming solution will be equal to the maximum possible answer to the given problem if both selected vertices A and B are located in the subtree with root at C. A big subarray will also be introduced. Big sub. This will be the maximum number of connected components that can be obtained from the subtree with root at C if one of the selected vertices is in it and the other is not. So conditionally, we chose vertex A in this subtree, while vertex B will be located somewhere outside of this subtree. And we will learn from A through our tree and go along the chain of removable vertices. We will count how much this will result in the connected component below. I'll show you the drawings. How is this going to happen? Well, both X and U are the two largest big sub values among children. We will need the vertices to calculate the recurrent forms, meaning we will store the two largest values for each vertex. Big sub and among the children using this thing is already painted in that. Let's choose our A and B. So let's say it will be shorter to store it here. Here possibly in a way that could be considered for the subtree in this context. Let's consider how this will actually happen. So let's say we have this scary thing here. From 15 vertices, we need to find the dynamic programming solution for the 100th vertex. In fact, what you have is the dynamic programming solution, and there should be some path going through vertex 6 in the subtree, and the whole vertex 6, so that the maximum possible answer occurs under this condition. So what would be the optimal option here to choose two vertices A and B within the subtree of vertex 6? Here, it's from that, and we hang it down from one to the other, and this will be the subtree of vertex 6. So what would the answers be for it? And which red vertices are in this subtree? And which vertices? If we remove a certain vertex, then it will immediately fall off. Among the children, there are many connectivity components. Which vertices will those be? If you remove a certain vertex, it will fall off. Many components. These are vertices 13 and 6. Among the children, there are many connectivity components. Which vertices will those be? These will be the vertices, namely 13 and 6. So if we remove 13, we immediately get these two connectivity components. Well, and plus this one at least appears right away. It depends on how we continue the path. With 6, at least two components appear right away, immediately making two vertices potentially A or B. This option will be one of the cases of optimal selection. But since it's possible here, so in fact this option will be one of the cases of optimal selection. So we remove 6 and 13, everything that is between them. And between them is only 7. So what connectivity components do we have? 50, 9. These three guys here, and what is above also becomes a separate connectivity component. In the end, the answer for 6 is 6. If we take the initial case, we can choose 10 or 11 and still get 6. So we can choose this vertex or that one and still have it. And we will also get 6. So we can either choose this vertex or that one, and we will still have it. dp, here it equals 6. And this is the answer for the subtask, as it turns out. And for the subtask with the big sub, we need to figure out what should happen. We need to choose vertex. Yes, find the big sub for vertex 1. The answer we have is for subtree 1. We need to choose a cheap way to hide something so that, for example, we choose like this. We got the maximum number of connectivity components. We need to choose something to hide cheaply, for example, like this. So everything was removed. And as a result, we got the maximum number of connected components. So this question should be answered by big sub. How can we do this for such a case? Which vertex should we choose to start from in order to reach one? We remove all these paths and get the maximum number of connectivity components, which is 6. We color the 6 and remove it. So we will remove it like this and get the connectivity components 1, 2, 3, 4, 5. You can see me here, but there's no way to survive the fight here. We need to use the development. If we don't tie in the 6, it won't be used. It should be like that, and it was enough for us. If we don't tie in the 6, then it definitely won't be used in any way. But it should be like that, and that was enough for us. So here's the symbolic answer. Here it will be 5. Actually, we need to conduct it 1 to 5 times. It's a color like that. Basically, there was one way to choose vertex for player 1. Well, once.
Want to become a great programmer? Subscribe to our Telegram channel.